Alright, y'all, this is chapter 4, Elements and Symbols, and we're going to be talking about atomic structure. So moving forward, we're going to start with a quote. "It is a slightly arresting notion that if you were to pick yourself apart with tweezers one atom at a time, you'd produce a mound of fine atomic dust, none of which had ever been alive, but all of which had once been you." And so we are all made of atoms, everything is made of atoms. And then I would like for you to, if you want to, watch this video. Go into the slides and you can watch this video. I don't know how to successfully video within a video, but if you click on the slides, you can watch this video about the size of an atom, and it really helps kind of get the size and density of the atom really down in your mind as like something meaningful, that it is very, 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 very small. So the main subatomic particles of the atom that we're going to be talking about are the protons, the neutrons, and the electrons. We're going to be looking at protons and abbreviating them as P+. We're going to abbreviate neutrons as N0 and electrons as E-. And I'm going to be using these abbreviations because of the charges. So the charges of protons, neutrons, and electrons are +1, 0, and -1 respectively. And your masses, I would like for you to look at these masses. The protons and neutrons both have a mass of around 1, but the electrons have a very, very small mass. And so because their mass is so much less than 1, we will say that this mass is close to 0. And so we'll just say that it's negligible, meaning that we're just not going to count it. Does it have mass? Yes, it has mass, but we're not going to count it as mass when we're doing mass number math. The protons and neutrons are in the nucleus, and the electrons are floating around outside. And the video in the previous slide makes it a lot easier because it gives you a great visual for this. So moving backward in time, we're just going to do a quick spiel for history of the atom. So we first thought of the idea of the atom, Democritus and Leucippus, back in ancient times, thought about if you were to take something apart many, many times, kind of like thinking about cutting something in half over and over again, eventually you get to a part that you cannot cut any longer because it's too small. So we're going to call that atomos, meaning indivisible. That's where the word atom comes from. So fast forward from ancient times all the way to 1808, we get the modern atomic theory from John Dalton. So John said that each element is composed of atoms, and those atoms are indestructible. All atoms of a given element are essentially the same, and atoms combine in simple whole number ratios to form compounds. And so this is the modern atomic theory. This is the model that everything else is kind of built on, and then we kind of get more specific and more specific as we go about what's inside of an atom and how does it behave. We've gotten so far in the idea of atoms that we can now actually see them, and so in our last slide you've seen the atoms, but here's another image of that. You can see the xenon atoms as little bumps forming the letters IBM, and so IBM made this, and we can move the atoms around and have them deposited in certain places. So about 100 years later, after Dalton's model, J.J. Thomson comes along and essentially discovers the electron. And so in his discovery, he used the cathode ray tube experiment. What he found is that the particles that he was shooting through this cathode ray, he was passing these particles through, and they were, he put a plate on the end of the cathode ray tube, and so let's just assume that this plate is a positive plate. And he saw that the energy would curl toward the positive plate. If it's curling towards positive, it must be negative, right? And so he kind of discovered the electron, and what he thought was the electron is plopped around like raisins in raisin toast or plums in plum pudding. So here are the electrons kind of plopped around, and then the whole thing is just some positive charge because he knew that atoms were neutral. So if you got to have something negative, you got to have something positive as well. So a few years later, Rutherford came along and actually said, well, I don't really think the model of the atom looks like that. And so Rutherford discovered a dense positive nucleus here, and this dense positive nucleus, and the electrons must be kind of floating around. So he discovered the positive nucleus using the gold foil experiment. The gold foil experiment essentially works like this. I take positive particles and I shoot the positive particles through the gold foil, and I would expect them to go through the gold foil if this were the model of the atom. So look at that plum pudding model. So I would expect that. But what I really see is the particles being deflected by something, and I'm shooting alpha particles, which are positive particles. So I'm shooting positive particles at the foil. Some of them are being deflected. So what can repel positive? But positive. So we have a positive nucleus repelling these positive particles, and we get this sort of pattern. So he discovered that the nucleus is very dense, very small, and positively charged. So here's our current model of the atom. We have the electrons kind of floating around in some sort of space, and then we have everything else in the nucleus making it very dense and positive. Alright, so we're going to look at this simulation, which I need to actually pull up. Okay, and you can play with the simulation at home as well. I have linked it in your Canvas. It's also linked in the slides. So if you click on the atom, as we build the atom, what I want you to do is open up everything, and then we're going to move protons and neutrons and electrons into the atom. So we know that atoms, that electrons don't really orbit like this. They actually go into a cloud, but if you kind of look at the cloud, it's kind of hard to see what's going on in there. So I prefer that you guys use the orbit model, and that will be a lot easier. And so let's just throw some protons, neutrons, and electrons in, and I want you to tell me what you see changing on the right side of the screen as we move those things. And so we'll kind of look at this simulation. As I put in protons, what is changing? Right, so you should have noticed that when I put protons in, that the element changes its identity, that the charge changes, and the mass changes. So the proton changes everything. Now let's look at the neutrons. So the neutrons do not change the element, they do not change the charge, but if we click on this little button, stable, unstable, let's look and see if the neutrons can help us with something. So this beryllium atom is very unstable. So unstable means it's going to be radioactive, meaning that it's going to become more stable by changing its actual nucleus, and it's going to give off energy when it does that. And so if we're looking at this beryllium, if we add more neutrons, we become stable, and then if we add too many neutrons, then we can become unstable. And so the number of neutrons will affect the mass and also affect the stability of the atom. But that's a little too crazy to keep on, so we'll turn that off. Now we're going to look at electrons. So what do you think will happen when I move the electrons around? So let's take a peek. So my electrons are going to not go into the nucleus, they're going to go into the outer shell, or to the orbits. See that we can only put 2 in the first orbit, not 3. That's interesting. And then as I move the electrons, we're changing the charge, which makes sense because electrons have a charge. You can fit 2 in the first orbital, and you can fit, or orbit, and you can fit 8 in the second orbit. If the protons and the protons and electrons are equal, you have a neutral atom. The net charge is 0. And if you have a beryllium with a different mass, we call that an isotope. And so we will talk about that in a minute. So moving into the symbol range of this simulation, which I encourage you to play around in all of these, we're going to use this symbol notation to tell us the different parts of the atom. And so kind of just throwing some protons in, what do we see change? We see the element change, we see the mass change, and we see the charge change. And so the proton number of 6 is going to be seen in the bottom left of this, and the element identity is in the center of carbon. If I add neutrons, we see that it's going to affect the mass. And so this carbon would be carbon, let's do 14. And so a mass of 14 does not mean 14 neutrons, it means 14 protons and neutrons total in the nucleus. So the mass is going to be the total number of protons and neutrons in the nucleus, whereas the bottom left number is only the protons. The top right number tells us the charge, and so if we wanted to make a neutral carbon, we would need 6 protons, 6 electrons. If we wanted to make a carbon that had a negative charge, we'd add more electrons. And if we wanted to make a carbon with a positive charge, we'd take away electrons. Notice that I didn't add a proton to make the carbon more positive, because if you add a proton, you change the element's name. So to make an atom positive, you have to remove electrons. To make it negative, you add electrons. So we can't really change the element, so you have to play around with the charge by playing with the electrons. I encourage you to play the game. It can help you with just counting these things, and it's a good way to practice. Okay, so that was that simulation. It's linked in the slides and also linked on Canvas for you. And so looking at some of these terms that we looked at in the simulation, the number of protons is going to be equal to the atomic number. And so your atomic number is the number of protons. When you're looking on the periodic table, you will typically see the atomic number at the top of the periodic table. The number of protons is also the identity of the element. So sodium particles always have 11 protons, an atomic number of 11. So here this is showing you 3 protons are always a lithium and 6 protons are always a carbon. Looking at our charge, for neutral atoms, the net charge is 0. So the number of protons is equal to the number of electrons. You will always assume neutral unless you are told otherwise. If you are told otherwise, for a charge, you will need to take the protons and subtract the electrons, and we'll do more practice with this in class. And lastly, the mass number represents the number of particles in the nucleus as a total. It is always a whole number. You cannot have half of a proton or half of a neutron, and so you will add up number of protons and number of neutrons to get the mass number. Another thing to note about this, sorry I'm moving around, does not appear in the periodic table. So the mass number does not appear in the periodic table, is the average atomic mass. It's a weighted average that appears in the periodic table. The weighted average can be rounded to give an average mass, but your mass number and your average mass on the periodic table do not have to be the same. So let's do a little practice. Zinc, a micromineral, is needed for metabolic reactions in cells, DNA synthesis, and the growth of bones, teeth, and connective tissue, and the proper functioning of the immune system. For an atom of zinc that has a mass number of 68, determine the following: number of protons, neutrons, and electrons. So pause and then come back. So I see in my periodic table, and I'm going to use yours located here in Canvas for you under the Intro Important Info tab. And so we're seeing zinc here is 65.39 mass and 30 atomic number. And so moving back here, the number of protons, so remember zinc was 30, Zn 65.39, I believe. So the number of protons are equal to the atomic number. The atomic number for zinc is 30. The number of neutrons is equal to, I need to find the mass for that, so the mass number is equal to protons plus neutrons. And so the mass number, we can look at the average atomic mass. We have to round this to a whole number. So to round this to a whole number for the average mass, oh wait, though they are actually telling me about a mass, sorry, they're telling me about a mass of 68, my bad. And so the question is asking me to find the atom of zinc that has a mass of 68. Now, this is 65, but that's totally fine because this is the average. Not every zinc atom has to have an average of 65. You can have a zinc atom that's a little heavier that has 68, and that is totally fine. And so our zinc is 68. If our mass is 68 and our protons are 30, what's your neutrons? Now, if you want to solve for n, subtract both sides by 30. You can do that. No shame in doing that. So we see we have neutrons of 38. Now electrons, do they tell me anything about the charge in the question? The answer is no, then we are always going to assume neutral. In that case, number of protons and number of electrons is the same. So I mentioned a term in the simulation called an isotope. An isotope is the same element, but it has different masses or different numbers of neutrons. So same element, which means it has the same protons, sorry, my pen is really lagging here. Wow. Come on, same protons, but different neutrons. No. Sorry guys, my app is being really slow. Different neutrons, therefore a different mass. So that's what an isotope is. And you can see that neon here has 3 different isotopes. It has an isotope of 20, mass of 20, an isotope with a mass of 22, and an isotope with a mass of 21. You could figure out how many neutrons that is by looking at the atomic number and making sure it adds up to get that mass. What is the most stable isotope of neon? So if we look at a direct sample of neon, we see that 90% is neon 20. So neon 20 must be the most stable because it is the most prevalent. And nature will always do that. The most stable version is the one that's going to happen the most. The least stable isotope of neon is going to be whatever is the 0.27%, which is your neon 21. That's not quite as stable. And so we looked at this in the simulation as well, but isotope notation gives you a mass number on the top, atomic number on the bottom left, chemical symbol in the middle, and then if you wanted to, you could put a charge right in here. And that is what I mean when I say isotope notation on an exam. And so given these isotope notations, we'll determine the number of protons, neutrons, and electrons. And you're more than welcome to work on this and then check your answers in these slides. Moving along to the periodic table. The periodic table, you will have a blank one. It does not have colors like this. It does not differentiate your metals and your nonmetals, but you do need to know, essentially you also need to know where this zigzag line occurs. And so know that it starts at Bal, in between boron and aluminum is where it starts. On the left side of the line, you see we have all metals. On the right side of the line, we see we have nonmetals. And then along this line, we have these things that we call metalloids, meaning that they are not metals and they are not really nonmetals. They're kind of in between. Don't forget about hydrogen over here acting as a nonmetal, but hanging out on the left side with the rest of the metals. So my boy Dmitry Mendeleev came up with the periodic table. He put into place a lot of ideas that other people just couldn't really figure out. And his periodic table was great because it allowed us to predict predict unknown elements at the time. If you click on this picture here in these slides, it will take you to a great little video, a little history about the periodic table and why it is so awesome. And I will continue to sing the praises of the periodic table and my boy Dmitry throughout our course. So get really familiar with the periodic table. Hopefully you've been memorizing those elements. Yeah, the periodic table is great. Use it as much as you can. So, metals. They're on the left side of the periodic table. My metals are ductile. Ductile means I can pull it into a wire. I can turn a metal into a wire. How do I know that? Because I have copper wires and things inside of all my electricity. I have wires of aluminum, and you have wires of different types of metal, right? Nichrome and things like that. So you have a ductile. They are malleable. meaning you can hammer them into a sheet. You guys have ever used aluminum foil, then you know that aluminum is malleable. I can hammer it into a sheet and it can be moved around like that. Usually your metals are shiny, so also think about some aluminum foil, shiny metals. Gold, for example, is a metal, right? So it's super shiny. It's a good conductor of heat. So we have a low specific heat because it's easy to change its temperature. And it's also a good conductor of electricity because the electrons in a metal kind of hang out with each other. We call that a sea of electrons that happens there. Okay. Alright, so these are some points about metals. Nonmetals are the opposite of metals. Nonmetals. They're on the right side of the periodic table. Your nonmetals are, they're very brittle, so they will break. I want you to think about your graphite and your pencil. So graphite in your pencil is pure carbon. And so that's what I want you to think about as a nonmetal, right? Can graphite be kind of shiny? Sure. Can we use graphite to conduct electricity? Sometimes. But I want you to think about the brittleness of that graphite in your pencil as kind of a typical nonmetal. So bad conductors in general. And a nonmetal can be solid, liquid, or gas. We have all of them, and we'll talk more about those as we go through in the class and identifying those. So you have a solid, liquid, or gas. You have one liquid nonmetal, which is bromine, is a liquid. Going back up to metals really quick, you have most metals are solids. And there's one liquid. Anybody know the liquid metal? Yeah. Mercury is liquid. That is your one liquid metal. Most metals are solid. Then in the middle here we have these really weird things, these metalloids. They're all along the zigzag line except for aluminum. Aluminum we consider a full-on metal. These metalloids, like silicon is your poster child for a metalloid. So silicon has different conductivity at higher temperatures. Most metals lose their conductivity at higher temperatures. But if I'm trying to conduct electricity in my phone, I want it to run well in high temperatures. And so I use these silicon computer chips to help maintain my electrical appliances and things at high temperatures. And so Silicon Valley is named after this silicon, not silicone. Silicone is plastic, silicon is the metal, and that is the metalloid that we use. So that's your kind of poster child metalloid there. Some groups and families that I want you to know. You need to know where the alkali metals are. This is your group 1, guys. Okay, right under hydrogen, we don't consider hydrogen a metal, so it doesn't get to live in that family, but it's in the same group, but we don't call it the alkali metal, so an alkali metal here. Alkaline earth metals, they are your group 2s. You have your halogens, they are group 7 or 17, depending on what periodic table you're looking at, and then you have your noble gases, group 8 or 18. And if you look at your periodic table, they are your alkali metals, your alkaline earth metals, your halogens, and your noble gases. So here are some common ions. So ions are charged particles. They have different numbers of protons and different numbers of electrons than normal. And you have a lot of positive ions on the left side. Most metals make positive ions when they make ions, meaning that they lose electrons to make ions. And you have over on the right side, we see our nonmetals typically make negative ions, meaning that they gain electrons to become more stable. And that's going to mean something when we get into chapter 6. But for right now, let's look at the trends. Do we see in group 1 how they're all +1? Cool. At the top of group 1 on your periodic table that you're using for studying or that you're using for notes, not the one you're using for studying, the one you use for studying is staying blank, but maybe another one you want to write in your notes, put a little +1 up here. So these elements, when they make a charge, not that they are charged all the time, but when they decide to make a charge, for stability reasons, they will lose 1 electron, becoming +1. Your alkaline earth metals will lose 2 electrons to become +2. Your aluminum family over here are mostly +3s. I only want you to remember these two are +3s, okay? Your nitrogens are -3s, your oxygens -2s, and your halogens -1 when they make a charge. There's a couple others I want you to memorize the charge of. And so we have aluminum and gallium here, and I want you to remember these two. This one is good old zinc, and this one is cadmium. These are both +2. And then one more to memorize, I know you have so much to memorize, I'm sorry, is silver, and silver is always a +1. So you have +2, well, +1, +2, +3, +2, +1. So kind of going up and going back down, and then you also have your negatives on the right side, and then the charge of the noble gases is going to be 0 because they don't need to do anything to be perfect. Noble gases are already in their most stable form. That's why we call them noble. They don't interact with anybody else. You do not need to memorize this. If you see a question and the homework accidentally snuck in there asking you about macrominerals and microminerals and memorizing them, you do not need to memorize that. It is just for you to know going into healthcare. Major elements in the human body are CHON, C-H-O-N. That is the major elements of any organic compounds. You have your macrominerals that are in the body more often: sodium, magnesium, calcium, potassium, phosphorus, sulfur, and chlorine. And then you have your trace elements of things that we still need, but we don't have as much of them. So those are just some common elements and ions, and they're not just pure elements. We don't have pure sodium in our bodies. We have sodium ions in our bodies, and we'll talk more about that when we get into those electrons. Alright, so, oh no, my slide doesn't work like this. So I have a slide that shows some pictures, and this is a PDF, so it won't work. So the Hindenburg, I don't know if you guys know about the Hindenburg, but the Hindenburg was a blimp, and it exploded, and it was full of hydrogen gas. And hydrogen gas is very, very, very flammable. And so you have 1 proton hanging out in hydrogen with 1 electron hanging out in the end. Versus modern day blimps is what this says over here. So modern day blimps are made with helium, and helium has 2 protons, 2 neutrons, and 2 electrons. So what's the difference between these two? Helium is a noble gas. It's noble, not reactive, not doing anything with anyone because it's all set. Versus hydrogen is in the alkali metal group, meaning that it is going to be much more reactive. And so that hydrogen is super flammable, but helium is a noble gas. And all we did was add 1 more proton, some neutrons, and 1 more electron. But the main thing that affects the reactivity is the electron configuration, which means the arrangement of electrons. So my reactivity is really defined by my electron configuration versus my nuclear stability is defined by my neutron to proton ratio. So to talk about electrons, first we have to talk about light, because to get into what's going on with electrons, Niels Bohr of the Bohr model, he really looked at how different elements gave off different lights. And so in this example, we see that the element barium over here is giving off a green light. And that means that we can see this green light, but if you filter this green light through a prism, we actually find that this is what barium is giving off. It's giving off these specific different wavelengths of colors, these specific light colors, and you can actually identify an element based on its spectrum. So every element has a different combination of lines and colors that it will give off when you excite it and pass it through a prism. So this is how we can use telescopes to see stars and tell what elements are being prevalent or are prevalent in that star, and tell whether or not the star is a young star, or it's dying, or it has already died. And by the time, of course, that light gets to us, that star's probably dead anyway. But we can at least filter through the light and try to tell what was going on at that star when the light was being sent to us. So how do we do this? We heat up or we excite the particles. We have to excite these particles and their electrons start moving around. Those electrons start moving around and they give off energy as light. So we see an atomic emission spectrum and we see white light looking like this with all the colors like a rainbow. Hydrogen gives off these 4 little lines. Helium gives off more lines. I have more electrons, I give off more lines, and then neon gives off a whole lot of lines. And so this is filtering through a prism the light that those elements gives off. Okay, so looking at these would give us something like this if we look through a prism. And so we need to frame this in the electromagnetic spectrum. So what we're seeing is visible light, which is this tiny portion of the whole electromagnetic spectrum. So when a scientist says the word light, we mean this whole thing, the electromagnetic spectrum. But when we colloquially say light, we're just talking about visible light, correct? We're talking about Roy G. Biv. So look at our light. Red is here, orange, green, blue, and violet. Roy G. Biv. We got the indigo out of there because indigo is not a separate color, we decided. And so now we have Roy G. Biv instead of Roy G. Biv. So let's think about the energy of these different waves of light. So light travels as a wave, but it hits things as a particle. So there's a particle of light called a photon. Photon is a particle of light. Kind of like photography, right? And so a photon is a particle of light, and we can look at the different wavelengths and frequencies of this light. So you're thinking right now, what does this have to do with the structure of the atom? Well, electrons behave a lot like photons, and electrons moving around gives us light. So we have to kind of know, well, what does that tell us about the electron if elements are sending off light? We need to be able to analyze that. So if we look down here at our radio waves, there are lowest energy waves. And so check my wave out down here. If we were on a boat on this wave, forgive me, but yes, I'm going to draw us on a boat. We have a hat. Maybe we have a little flag on our boats. This is a nice relaxing day on the ocean. So this is a low energy wave. This is low energy. Whoops. This is a low energy wave. So looking at my wavelength, as you go this way, going from 3 to 4 to 5 exponent, is getting greater. So this is a long wavelength. So low energy, long wavelength. And look at our frequency though. As we go this way, your frequency gets smaller. So the amount of times per second you're bobbing up and down. If you have a long wavelength, your frequency is low because we're not bobbing up and down very much. And if you notice this frequency, the unit is in hertz. And if you've ever looked closely at your radio stations, you will see hertz as the dial changes. The hertz is the unit of those numbers on your radio stations. So building more energy, our wavelengths are getting shorter. And so we have power lines of radio waves, we have obviously AM, FM radio, moving up to television, cell phones, we get into the microwave region. And so comparing these waves, I'm starting to get a little shorter wavelength here in microwave. And so I'm getting higher energy, so my energy is increasing. And then we move from microwaves through satellite to infrared. Infrared is heat energy, and you are giving this radiation off right now because everyone gives off heat. So infrared is more energy than microwave. And then we have under infrared. So think about what this means, this word. Infrared literally means under red. So what color comes first? Red. Right? Below red, infrared, the color that comes first is red. So we're going increasing energy as we go. So which color has the lowest energy? Yeah, red. So red has the lowest energy. It also, if we look at these numbers, red has the highest, longest wavelength. So long waves, low energy. Short waves, high energy. So let's continue our journey here. We have visible light. Now actually this is kind of wrong. The sun gives off all of this radiation. Our atmosphere just blocks most of it. That's bad, so blocking the higher energy stuff. So ultraviolet. Again, what do you think ultraviolet is? Above violet. So ultraviolet's above violet. Getting up here, we get into X-rays, and then we have gamma. Now, if you can imagine us on a boat, on this wave, over here. Well, I didn't keep it together for too long. So my boat's over here, my flag's over here. I'm flying through the air, probably not having a good time anymore. My hat's all over here. So if I'm on these waves, I'm not having a nice relaxing time. So what is my energy like? I have high energy. What is my wavelength like? Well, my wavelength 10 to the negative 11 is really short. So short wavelength. And my frequency is a high frequency. There's a high amount of bobbing up and down really fast. So you can think about your energy and frequency being directly related and your energy and wavelength being indirectly related. So the highest energy light color is violet. The lowest energy is red. So we're looking back at my hydrogen. I have some electrons that are giving off high energy, and I have some electrons that are giving off pretty low energies. And I can tell how the electron is moving based on the energy it gives off. So the Bohr model is developed from these observations. So what is going on? I want you to think about the atom, a Bohr model. I'm looking at this guy. So you may be familiar with this model, right? Where we have these rings around the nucleus and we have these ends. Your ends are your energy levels. And so our energy levels are essentially telling us how far away we are from the nucleus. So low energy is close to the nucleus and high energy is far away from the nucleus. Electrons want to be close to the nucleus because electrons are negative and nucleus is positive, so they're attracted to each other. So low energy means that we are close to where we want to be. We're close to the thing that we're attracted to, so we're relaxed. And so moving back up here really quickly, our ends are your energy levels. And so the higher up you get, the more energy you have. And so how do you make an electron go from low energy to high energy? Well, you have to give it energy. And so when we're talking about these Bohr models, or how Bohr came up with this, he was exciting electrons. And so what we do is we heat it up, or give it some electricity. The electron moves up an energy level. Then the electron doesn't want to be at that high energy because it is attracted to the nucleus. The electron wants to move back down to a low energy level. When it does that, we emit light. The certain wavelength means a certain color. So a long wavelength means red, low energy. A higher energy means green, blue, violet. And so look at the difference here between these two. This electron isn't moving very far, and this electron is moving very far. So this electron's moving a lot farther, meaning it makes a higher energy wave. If you look in the slides, it's a nice little GIF kind of showing you that. And so from that, Bohr said, hey, I think these electrons are hanging out in these specific energy levels because they're giving off these very specific colors of light, which makes total sense. What I want you to know about this, though, is that when you put energy in, the electron moves up, and when the electron moves down, it gives off energy. So see here, we can see that we're getting our energy from an electron moving down back to what we call a ground state. So that's where we get this energy emitting. So again, here's your electromagnetic spectrum. Kind of a simpler slide if you wanted to kind of refer to this one in your notes. This one is a little simpler than the previous one, just kind of showing you that wavelength and your different energies and your different types of radiation. Okay, so Bohr's model is a gray model and we still use it, but it's not quite accurate. Electrons don't hang around in those rings around the nucleus. Electrons are kind of crazy. So electrons are kind of unpredictable. And so if I'm the catcher of a baseball game, then I can not tell you exactly where that ball is going to hit my glove, but I can tell you with likelihood that given the trajectory of the pitch, that is statistically probable that it would hit here or here because that's where the pitcher is trying to throw it, right? Versus different probabilities for outside of this zone. And so we can develop a probability map of if I throw the ball 100 times in the same way, where does the ball wind up? Then you have a probability map of where it's probably going to be. Electrons are kind of the same way. We have to test these different areas of electrons to see, okay, where are these things located? Because they're so small and they're constantly moving, we have to stop them to see how fast they're going, and we have to, we have to stop them to see where they are, and we have to let them go to see how fast they're going. So we can't know both where they are and how fast they're going at the same time. That's called the Heisenberg uncertainty principle. So if you've watched Breaking Bad, you've heard the name Heisenberg before. So we get these probability maps of where electrons are probably located. And we have these different names for these different shapes. And so our first name is S. So we call these orbitals these different shapes. And so we're going to call this spherical shape S. And so the energy is the big number. So in the first levels, I want you to think about Bohr's model, energy 1. Energy 2, and energy 3, right? So same idea. We do agree with Bohr. Yes, there are energies, but we don't think that there's like these orbitals, these electrons on a line like planets around the sun. We think these electrons are probably in this shaded area here somewhere, but that doesn't mean that they have to be in that area. They're just probably there. And so you have your first energy level sphere, S. Then you have built on top of that second energy level S and third energy level S, depending on how many electrons you have. Each shape holds 2 electrons. So I can fit 2 electrons in any of these given shapes. Okay. So this is one shape. We're going to get way more complicated than this, don't worry. So one shape of possibility, of probability, is that you have this S. This is the lowest energy, most stable shape to be in. We get a little more complicated, we are going to get into the P shape. So these P orbitals, we have Px, Py, and Pz. 3 dimensions, so we have 3 different shapes in each 3-dimensional relationship. And so combining these p orbitals around the nucleus would look kind of like this floral thing over here. But if you're a p electron, you're probably in one of these kind of dumbbell shapes. There are 3 p's per energy level. If you look back at the S, there's only 1 S per energy level. But here there are 3 p's per energy. Again, 2 electrons per shape. So how many total electrons in a p? Well, if there are 3 shapes, 2 electrons per shape, 6 total electrons can live in 1 p orbital. Now we have the d orbitals. D orbital has 5 different shapes, kind of like combinations of p, and then this one down here that's like hula hooping. You have your d orbitals, so 5 different shapes, 2 electrons per shape, 10 total electrons for your d orbital. And then this is the f orbital. And f orbitals get a little crazy. There are 1, 2, 3, 4, 5, 6, 7 shapes, so 14 total electrons can live in an f orbital. Okay. So you've got these crazy shapes. They're probability maps, just like that baseball probability map that I showed you. And they're essentially telling us where we think a certain type of electron is going to be. How do these electrons exist in such a small space in the same shape? Electrons are both negative. They repel each other. So they exist by spinning in opposite directions. And so you can have two electrons hanging out in one shape, but one is going to spin clockwise and the other is going to spin counterclockwise. And so we will come back to this idea in how we denote these electrons in just a minute, but this is something that is happening in there. That's how they fit in that small little space. So here's a nice little chart to sum up what we talked about, how many electrons can go in that space and how many different shapes you have per energy. So in our first energy level, N, we only have one type of shape, which is S, and so 2 total electrons. In our second energy level, we have 2 different types of shapes, one P, one S. P has 3, which has 6 electrons, and S has 1, which can have 2, so a total of 8 electrons. For the third energy level, we add the D electrons, so 18 total in the third energy. And for the fourth energy level, we have all systems running, so a total of 32 electrons can fit in the fourth energy level total, divided into each of these different shapes. You're going to ask me, do I have to memorize this? The answer is no, because your periodic table is amazing, and your periodic table has it already in there for you, even though Mendeleev didn't know any of this stuff when he made the periodic table in the first place. So let's check this out. If you break your periodic table into sections, we're going to call them blocks. S, P, D, and F block. So making a quick note, helium is really an S block. So remember, helium belongs in S. Helium used to be an alkaline earth metal, but we decided that helium was too fancy for that, so helium is now a noble gas because helium is super stable. Alright, so these are your blocks, S in blue. We have our D block in orange, pink is for P, and we have our F block down here in green. Now, you remember me telling you about the total electrons that can be in each of these weird shapes? Well, you don't have to memorize that, because if you look at the thickness of the block, how many squares thick is S? It's 2 thick, so 2 total electrons fit in S. How many squares thick is D? Well, it's 10. What about P? 6. What about F? 14. So if you just count across, you know how many electrons can fit in that orbital. But what about how many shapes are in that orbital? Well, each shape holds 2 electrons. And so if I'm looking at P here, and I count 6 electrons, how many shapes? Divided by 2, 3 shapes total in the P. So you never have to memorize this. You can always look at the periodic table to tell how many shapes and how many electrons you can fit in these specific orbitals. And so, how do we use this? What do electron configurations tell us? Electron configurations tell us how many electrons are where, and that can tell us then how the element might behave. And so we have different ways of looking at the electron configurations. So first I'm just going to show you what an electron configuration looks like, and then I'm going to show you how to use the periodic table to find it. So 3 things in electron configuration. First, you have your orbital, that's the letter, and the orbital kind of comes with an energy level. So orbital comes with the energy level, so that's a 1s orbital, or a 2s, or a 3s, etc. And then there's a little number at the top, a superscript, kind of like Superman flying in the sky, got a superscript up at the top, telling me the number of electrons that are in that orbital. So they're, for hydrogen, 1 electron in the 1s. So let's go back to our periodic table. What can we correlate to the S? Well, hydrogen is chilling in the S block, so that is where I get the S from. Where do I get the energy level from? If you look at the period the hydrogen is in, it's in the first period. So I can say my period is equal to my energy level for some of my blocks. That's for S and P blocks. And then look at each square. So if this is S1, this is S2. Right? Because this is the first square in the 2s, and this is the second square in the 2s. And hydrogen only has 1, so it's just going to be 1s1, 1 electron. So what I want you to think about when you're using your periodic table is your period is equal to your energy, your big number in front, for your S and your P blocks. For D block, your energy is your period minus 1. Remember how we talked about how, look at where D shows up. D shows up in energy level 3. But if you look at the period here, the D block starts in energy level 4. But that can't be true because I know that this is where the D block starts at 3D. And so I have to use that rule that the period minus 1 is where my D block starts. So in your periodic table using for notes, 3D is where scandium is, and then 4D for yttrium, 5D for lanthanum, and 6D for actinium. Then the F block, the energy is a period minus 1, period minus 2. And so for the F block, I showed you that F starts at energy level 4. But if we look at the period for F, F actually fits in right here. So if we have 57 move to 58, wow, hold on. Okay, 57 moved to 58 here. I'm in the 6th energy level. So my F block is moving back 2 places. So we're going to call this the 4F and the 5F. So go ahead and label that in your periodic table so that you can do what I'm about to do next, which is give me an electron configuration for different elements in the periodic table. So I want you to think about an electron configuration as an address. So your address, you're going to start from hydrogen home, and you're going to tell me how to get to the element of choice. And so let's just look at, the first one I want you to look at in here, and you can do these separately. We're going to do more practice in class, but let's just pick oxygen. So let's do oxygen together on the slides, then we'll do more practice in class. So for oxygen, of course, I'm just going to get rid of some of these little notes. So for oxygen, first of all, I need to see how many electrons do I need. For oxygen, I need 8 electrons, and so I'm looking to make sure that I find 8 electrons. Ignore these numbers in here. So I'm going to tell you how to get to oxygen, but I have to assume that you only know hydrogen. And so we're going to start here with hydrogen, and we're going to go all the way till we get to oxygen. So hydrogen is in the 1st energy level, so I'm going to write 1. And it's in the S block, so I'm going to write S. And then how many different squares do I need to go through to get out of the 1s? Because I don't want to be in the 1s. I want to come over here to, well, this is the 2p, right? And so if I look over at this is number 1, so I look over at number 2, well, that's also S, so I'm going to say 1s2. If we stop here, this is helium. So 1s2 would be the configuration for helium. But I don't want helium, I want oxygen, so I need to keep moving on. So helium is number 2. What happens at number 3? Well, I move into the 2nd energy. So anytime you switch energy or you switch blocks, you got to rewrite it. So I have now, I'm in the S block, and I need to go through 1, 2 to get through it, so 2s2. If I stop here, I'm at beryllium. And so moving forward to number 5, this is a new block. So I can't say 2s3. I'm going to be looking around for the 3rd square in the 2s, and it only has 2 total thickness. And so I have to move over to the P block. It's the same energy, but it's P. So how many do I need to move through to get to oxygen? 1, 2, 3, 4. So this is 2p4. So the electron configuration for oxygen is 1s2, 2s2, 2p4. So get that in your notes, and we'll do more practice in class. If you want to do more practice here, check the slides for the answers. Another way I can represent it is orbital diagrams. So orbital diagrams are kind of just like electron configuration. So remember, electron configuration for hydrogen was 1s1. And so instead, though, of electrons being numbers, I'm going to turn the electrons into arrows. Remember, we talked about how electrons spin clockwise and counterclockwise. So we'll say that as an up or down spin. And so we typically will do all up spins first. So we're showing that electron spinning up in the clockwise direction or whatever. This is just a model for how we think electrons can exist. And so if we're looking at our oxygen as an example, remember oxygen was 1s2, 2s, 2s2, 2p4. So for an orbital diagram, every s gets one box. Every p gets how many boxes? How many shapes does a p have? A p has 3 shapes, so you get 3 boxes for a p. A d has 5. 5 shapes, so 5 boxes. And an f would have 14. So 14 electrons, so 7 boxes for 7 shapes. And so what I want you to do is build your boxes first. I know this doesn't make a lot of sense right now. We're going to do more practice in class, promise. So we're going to build our boxes first. So for oxygen, first we have a 1s. And so I'm going to build a box. Then I have a 2s. When I say build boxes, I mean build all the boxes. And then I have a 2p. So how many boxes for a p? Any p is 3 boxes. Now we're going to put our electrons in. And so how many in the 1s? Well, I see that there's 2. So I'm going to put 1 up and 1 down. And you can't really see that. Let me do this. So 1 up, 1 down, because that's 1s, 2. So now I have 2s2. So there's 1 up, 1 down. So that's just how the electrons have to be, one spinning up, one spinning down, in order for them to exist in that small space. And watch when I get to p. I'm going to put 4 electrons in. Now, you know electrons like to be close to the nucleus, so lowest energy possible. And so I'm going to fill starting with the 1s. So the 1s is going to get filled up totally first before the 2s gets filled up because I want low energy. Now the 2p, this is all the same energy, the 2p. And so if I have an option, would I rather be by myself or pair with someone else if I repel other electrons? I'd rather be by myself. And so if you have a situation with p, d, or f where you can put 1 electron in each box first, you have to. So I have 4 electrons left to give out. So watch how I put them in. 1, 2, 3, 4. We put each electron in its own little box before we pair them up for p, d, or f orbitals. So if you have yours like this, that is wrong for 2p4. Because there's actually a 3rd box. That's why I say draw your boxes first, because then you'll never mess that up. So here are some templates for the different boxes. You can kind of see what's going on with F as I move forward. As you gain energy levels, you gain one more type of orbital, and you can put your electrons in this, and this is a good practice if you just want to have like a template for that. They do it bottom up. I do it left to right because I think it saves space. So you can do it like I did, left to right, or you can do it bottom up, doesn't matter. As long as you draw the boxes, your P boxes have to be connected. Your D boxes have to be connected, and your electrons need to be shown as arrows up and down, and I prefer the half arrows versus the total arrow because that just takes too much time and too much space. So the rules we've been talking about this whole time, that if you want to see them written down, here they are. The off-bow principle, electrons fill lowest energy level first. So we fill this 1s. You may have seen this kind of crazy chart thing. I say use the periodic table, but if this makes sense to you and you want to use it, go for it. It's showing you how to fill up the electrons lowest energy first. Hund's rule. This is when we put 2 electrons separate before we pair them up. And the Pauli exclusion principle says no 2 electrons can be the same, so if they're going to be in the same box, one's got to spin up, one spins down, right? You already know this. Alright, so we're going to try some orbital diagrams. We're going to do these in class. You can also check these slides for answers for this one. And then again, here's another template so you can kind of use that. So a shortcut, let's say I'm doing a really big element like uranium, which is 92. I don't want to start at hydrogen and work all the way down to uranium. So you can start at a noble gas because it has a full electron configuration. It is totally filled up. If you look at what would filled up look like. And so if I look at, so this one is filled up. That's helium. But then this one is filled up. See how this is all the way filled up on the second energy level? Totally filled up. What about the next one? The third energy level. Totally filled up. So 1s2, well, this is the first energy level all filled up. That's helium. Second energy all filled up. That would be neon. Okay. Now the third energy is a little weird. We get it, argon is kind of half filled up, and then we have the 3D is enveloped in kryptons. But you get these like fully filled up, all the way filled up shapes. And so your noble gases are very stable because everything is full. It has everything it needs. It doesn't want anything. It doesn't want to get rid of anything. It's all set. And so we can use that as a checkpoint. And so we can say, hey, remember when you were all filled up at neon? We can just write neon in brackets, and then we can go on the outside of neon. And so if sodium's electron configuration looks like this, neon's looks like this. And so I'm just replacing all of this work with neon, and then only showing you what's outside of neon. So if we look back at the periodic table, and we look at sodium number 11, the noble gas that comes right before sodium is neon. So neon goes in brackets, and then sodium is in the third energy level, the S block, and it's the first one in there. So neon 3s1 is for sodium. So that's helpful if we're doing really large elements. Alright, one more thing I want you to get, and then I'm going to explain it better in class. Oh, here's some more examples showing you these things. Don't worry about these configurations. They do something called, don't worry about these configurations. They do something called promoting, and you're more than welcome to explore why this is the way it is. And we'll talk more about transition metals in class. But just getting the general idea down is what I need from you for the video. A valence electron is the electrons on the highest energy. And highest energy is on the outside. And so if you look here, our energy levels are 1, 2, or 3. What's the highest energy? 3. So how many electrons total in the 3? 4 valence electrons. Okay. You can also have electrons. We'll talk about this 3D. We've talked about it before, but that's how you would fill up 3D. So my highest energy, we have 1, 2, 3, or 4. Highest energy is 4. Total in the 4 is 2 plus 4, which is 6. And so selenium has 6 valence electrons. Your valence electrons go across the periodic table groups. Group 1, valence of 1. Group 2, valence of 2. Then you skip on over to boron, valence of 3, valence of 4, valence of 5, valence of 6, valence of 7, and valence of 8, except helium only has 2. And so you can remember your valence kind of like your charge, your common charges across the top of the tall groups. Okay, so here's another valence chart. We're going to talk about Lewis symbols in Chapter 6. Again, talked about Lewis symbols in Chapter 6. Periodic trends. 3 periodic trends you need to know. You need to know atomic size decreases as you go to the right of the periodic table. So I want you to think about fluorine as being your smallest. It is not the smallest, but I want you to think about fluorine as being the smallest. And then I even have my little francium down here. I want you to think of francium as being the largest as far as size. And we'll talk about this a little bit in class. Just remind me to do the periodic trends for you, and we'll kind of go over why in class, but this video is running long, so I'm going to make sure that it stops. Alright, you also need to know ionization energy. So atomic size, fluorine smallest, francium biggest. So as you go towards fluorine to the right and up, you get smaller. As you go towards francium down and to the left, you get bigger. The opposite is true for this thing called ionization energy. So ionization energy is the energy needed to remove an electron. So if I'm really small, if I'm really little, my electron is negative and my protons are positive. If I'm closer to the thing I'm attracted to, it's going to be harder to remove me. So if you're smaller, you have a lot of energy to remove. So I want you to think about fluorine as having the highest ionization and francium as having the lowest. If you're very big, the distance between the nucleus and the valence electron increases, so you've got your negative and your positive farther apart, less attracted to each other. So less energy needed to take away this electron than this electron. And then metallic character, I want you to think about metal character being what's more metallic. Well, I don't know, these metals over here or these non-metals over here, which is more metallic? The metals over here are more metallic than the non-metals at the top right. So as you go left, you get more metallic, and as you go down, you get more metallic, and as you go right, you get less metallic, right? Here's a chart summing all of that up for you, and I will go over some of this with you again in class, but thank you for watching. I know this video is really long. Sorry!